mean they will be equal amount, but there is a certain amount which one is bigger doesn't matter. They stay in the equivalent concentration, so you can define equivalent constant with product concentration over reactant concentration, right? The equivalent constant could be Ka or Kb or Ksp, something like that. But in this unit 2, we are looking at kinetics. Kinetics is about, instead of which one you have more like product or reactant, we are looking at how fast this reaction proceeds. It would mean either a forward reaction or backward reaction. Okay? How fast reaction proceeds. That's what chemical kinetics is. And then we're going to have to define how we're going to decide our reaction rate. Because when we say some reaction is fast or slow, we have to quantify. So we have to get the number, how fast that is. So that's what the reaction rate is. So why do we study reaction rate? Well, if you know that which reaction go faster, when later you just design a reactor. So if reaction goes faster, then you may design differently compared to reaction goes slower. Because if reaction goes fast, let's say you mix some compound A, compound B through certain pipe. You are designing a reactor in the macro scale. If reaction goes fast, then you have to provide reactant very fast, and then you have to take out product also very fast. You may use a smaller container, but with certain design that flow become fast, right? But if reaction goes slower, maybe you have to design containers bigger. So you have to decide how you're going to design it. So whether you are a chemical engineer, or a scientist, knowing reaction rate is very helpful. Also, that will relate to reaction mechanism. If reaction goes fast or slow, that indicate something happened behind this reaction. Okay? There is a 4 factors that affect reaction rate. Let's say you react with A and B. If they are like a heterogeneous mixture like this way, then reaction will happen only in the interface, which means that's where A and B meet, right? So this is what we call a heterogeneous or inhomogeneous. But if you mix A and B together in the same solution, then it's homogeneous. So then everywhere it's possible that A meets molecule B, so reaction will be faster. So homogeneity is one of the factors making reaction goes faster. Concentration. If you have a little bit of A or a little bit of B, there's a less chance to mix this molecule together compared to you have a large of A, B here, right? So higher concentration will definitely help reaction goes faster. That's another factor. Also temperature. The reason you can preserve food in the refrigerator is because at cold temperature it perishes a lot slower, right? So reaction goes slower. Increasing temperature will definitely accelerate reaction. It makes reaction go a lot faster. Another one is catalyst. Having a catalyst will help also reaction go faster. Those are 4 different factors affect reaction rate. So in Chem 2, everything is quantitative. Instead of saying reaction fast, slow, let's find some number. How are we going to define our reaction rate? As a simplest example, A turning to B. This might be simplest reaction. if that happen, reaction is defined by how quickly A convert to B, right? So given time, how constant change? So either you can say whenever reaction happen, constant B will increase. So how constant B change over time? That's your reaction rate. Or you could say same thing about the A because the rate produced B is actually same as A, the rate of consuming A. So you can say change of A over delta T is also related to reaction rate. But be careful. This will increase over time, but this constant will decrease. So although the number-wise will be same, this will be negative number. So you have to count with negative sign to make it they are equal. Okay? So that's how we define reaction rate. Now this delta means difference or change. So delta T means later time minus initial time. So time difference is delta T. Delta B is change in concentration. So delta B is, if you're not familiar, later concentration minus initial concentration. So that's how we're going to define reaction rate. Unit of reaction rate is, you can see on top of it, you see concentration, which means molar concentration. On the bottom, you have time. Normally we use second. So typical unit for reaction rate is molarity over second. Sometimes instead of molarity, they use mole over liter, which is the same thing. So reaction rate unit will be either that or mole over liter second. Either will be fine, because they mean the same thing. So with that definition of reaction rate is equal to delta B over delta T. Now you should know how we're going to detect change in concentration, right? How do we know you produce more B? Well, if reactant color is different from product color blue, then you see the change of color. So you can say constant change, but you can really quantify with your eye. So you may have to use spectrophotometer to get actual number. Or if reaction is produced from solid to gas, then you will see change in pressure, right? So in that case, you can just measure how pressure change. Sometimes reaction produce acid, like HCl. Okay, something reacted with something produces. I'm just making up. Produce acid. Okay. Then reactants probably include hydrogen. That will change pH. So you can monitor pH. That's another way to measure how reaction, how you measure the reaction rate. Okay. So this is how you do it. So in the previous slide, there's a multiple different way to monitor change in concentration. So let's assume we did that. And then you measure time. Over time, concentration change like this. Then reaction rate is, as we written, that is concentration change over time. And if you look at this guy, this is our reactant, and this is our product. And then we have reactant here. And the reactant concentration will decrease, right? Decrease. So in first 50 seconds, concentration change like this. Then if we use A instead of B, the reaction rate is actually this. So subtract later concentration and initial concentration here, divided by time difference, which means 50 seconds. So then you will get this number. Why this number? Because this will be negative, because you subtract bigger number, but we count with negative sign, it will make it positive. So this is reaction rate in this interval. Now, next reaction rate between the 50 second to 100 second, we have different concentration, so you have to calculate again. You find out reaction rate decrease. The reason is that as time goes on, you are using this the reactant will be used up. So you have less and less concentration of reactants available. So because you have less reactant, overall reaction rate will go down. So over time, average rate goes down. Okay?
I'm sorry, I have a question.
Yeah, go ahead.
So you put the quantity of, so 0.905, you subtract the mass that it was?
Mm-hmm.
Okay.
So rate of concentration minus initial concentration over time.
Oh, okay, just intuitively, I thought it would be initial minus the later one.
Now always when we say change delta, it's
Oh,
always
yeah, okay, we're just looking for the difference.
whatever the quantity is final minus initial.
If you did it the other way, you wouldn't have to put the minus in front of it.
You can do that. You can do that. As long as so if you keep thinking later, you will confuse yourself and then you end up having the wrong number. But as long as you remember, it's okay. Okay. Very okay. So the rate we just defined as rate as delta U over delta T is what we call average rate, average reaction rate. So what we did is in first 50 seconds, so this 100 seconds, so between 0 and 50 seconds, at 0 second you have this concentration, at 50 seconds you have that concentration. So we did change in y over change in x, which means slope of those 2 points. Okay? So that was, drawing is not that great. That was slope of between 2 points. So that's slope connecting 2 points. In mass term, that is secant line. Secant line. It's a slope, right? You don't have to know this because it's a mass term. But then, if we have different 2 points, you're gonna have different average rate, right? Between those 2 points. What if? So if slope means reaction rate, what about slope at 1 point right here? That's also reaction rate. But we call that as instantaneous reaction rate because reaction rate here is, we are not using any time gap. It's at one given time, that's the slope. So it will be instantaneous reaction rate. So this is what we call tangent line. Both tangent line, secant line give us a slope. Okay? So anytime then you have in x-axis you have time, in y-axis concentration, that slope is what we call reaction rate. Only difference is secant line connecting 2 different points is average reaction rate. Tangent line from one single point is what we call instantaneous reaction rate. Okay? That's the distinction between those two. Now, what's the initial rate? Initial rate is tangent line at initial point right here. This is slope. This slope is initial reaction rate. Okay? At time equals 0. And we mostly use average reaction rate and initial rate at CHEM 1. But later in a higher level chemistry, you may use instantaneous reaction rate. So here, mostly initial reaction rate and average reaction rate. That's we are focusing on. So what is the average reaction rate between 10 and 30 seconds? How do you do that? Do you see the number? In this reaction, reaction rate is defined by rate is
Can I ask a quick question about that
Sure.
last one?
Yeah.
For sig figs, did you base the two sig figs off of the concentration or off the time?
time. We have 3 sig pig here on the top.
Uh-huh.
On the bottom we have 2 sig pig.
Wouldn't it just be one though because there's no decimal point?
Yes, but when they say 30 seconds, 10 seconds, we actually mean actually I have to use a point.
Okay.
Yeah. Because when we say 11 seconds, 12 seconds, 30 seconds, normally we mean actually 0 as well.
Perfect.
But rigorously, I mean this is 1 second. You are right.
Okay.
On the practical, when we mean 30 seconds, we actually mean 0 as well.
Okay.
But I have to write. If I want to emphasize it, I have to use additional point.
Right.
So in this case, if you just use 1 sig pig, that will be accepted because that's more rigorously following the rule.
Okay.
That's more accurate.
Perfect. Thank you.
This is just in general, but if our rate is like, our values are going down, how come our answer isn't negative? Like our rate is just like continuously.
Let's go back. So consider this guy is actually from reactant. Because it's reactant, so I use delta A with delta T because reactant will go, constant will go down, you counter with the negative sign.
Oh, we're using this side, okay.
Yeah, because it specifies which molecule it is. It turned out it's a reactant. If they use C2H4 instead of this, you know that was product. Then you are not using negative sign. So this is relevant to what you asked. If you so reaction rate can be so you could monitor any of the molecule. Because sometimes it's easier to monitor one molecule than the other molecule. So you can choose anyone, that will be fine. Because maybe this has vivid color, I'm just making up, vivid color, or this is a gas somehow. So if one molecule may be easier to monitor. Then just stay with that molecule, and if that turns out to be a product, then it will be plus sign, because that will constantly increase. If that, your choice was from reactant, You can constantly go down using negative side. Okay? This is related to what you asked. What about reaction is having like a different coefficient? Okay? Now reaction rate is unique. Whatever you, so whether you just observe monitor oxygen or nitrogen or monoxide or dioxide, reaction rate is unique for each reaction. So it shouldn't be matter whatever you follow. Or let's say you just try to monitor oxygen. That's one of the product. So this will be your reaction rate. Okay. Product. So get the positive sign. Constantly increase over time. But someone else followed this guy instead of oxygen. Now, if you do this number will be different from that guy. Why? Anytime when you put one oxygen, you are putting two of this. So obviously it will be twice faster. Because it's twice faster, you have to divide by that number here. So that will be equal to this. So you do not say my reaction rate is, oh, I have product over time. This is not reaction rate. Okay? This is reaction rate. So if you just choose this molecule, divide by that 2. This is reaction rate. Someone else might use, I feel more comfortable following this guy. That's fine. You do this. Over time, it's from reactant to negative sign, and there's 2 there, divided by 2. This is the reaction rate. So any of choice, in the end, they will give you exactly the same number. As long as you just take into account the coefficient in the denominator, all 3 different choices give the exact same picture. So in general, if you have any, this is very arbitrary general reaction, then your reaction rate is, if you choose product D, delta D over delta T, divided by that coefficient. If you choose C, divided by that coefficient. If you choose this reactant, do that with the negative sign, because it's from reactant side, divided by D. So any of choice will be fine. You should get the same number. Okay? So this is your quiz. Because we didn't learn anything yet, we are having quiz now. In the beginning. you done?
Just might need
Right. Because we have to cover the rest of the slide. Let's do 3 more minutes. 3 more minutes. More seconds.
So you're
10 more
reacting
seconds.
with the hydrogen from water. So, oh, there is the reaction is strong, right? So
Okay, let's move on. Huh? No problem.
Mine wasn't saving. Oh, it worked.
이거? So we know how to calculate the reaction rate, okay? So let's look at this. So you did a similar problem just now. So if we are given, for example, this reaction rate for second guy is, if you use this reactant, delta SO5 over delta T over delta 1 over 2, this is equal to 1 over 4 delta NO2 and 2 over delta T over delta O2 over delta T. They should give all exam same number. Now, for secondary reaction, this guy, if this one is given as that number, we're gonna find out this guy. So which means I wrote equation already here, delta N2O4, which means that. So if this guy is given number as negative 0.02 molarity over second, they're asking value NO2 over delta T, which means they are asking what is this number. Okay? So I can see this number, if I plug in over here and the cancel sign divided by 2, that will be 0.001 equal to 1 over 4 question. So my question is times 4, 0.004, right? Unit was mole over second. That should find out other rate. That's not reaction rate, that's the rate. Okay. What is the rate of disappearance of hydrogen during this interval from in 50 seconds? So I can say disappearance hydrogen. So hydrogen disappear. That reaction rate is within 50 seconds. Concentration later is 0.00. Initial concentration is 0.500. That will give us this number. Production of ammonia. They are basically asking delta ammonia over delta T. This is what they ask, right? Production of ammonia.
I don't have that slide.
You don't have?
We don't have the slides.
Wow.
It copied the one from above it, below it, instead of giving us that.
Wait. So you have this guy
Twice.
twice?
Mhm.
Yeah. Oh, what happened? I'm sorry. Okay. Okay. I just upload the new version, including this guy. Okay. Right. Let's go ahead. So rate of production of this is because if I write reaction rate, that will be delta N2 over delta T with a negative. My mistake. So this equal to negative 1 over 3 delta H2 and equal to 1 over 2 NH3 over delta T, right? Any of this will give us reaction rate. So if they ask this number, so they are asking this number, and we found that disappearance of hydrogen concentrate, hydrogen, so that was this number as here. So we know, okay, right. So this is rate of disappearance of hydrogen. This is not reaction rate. You have to distinguish between reaction rate. This is reaction rate. The reaction rate should include this number that divided by coefficient. Okay? But when they say disappearance of hydrogen, not having that number. Okay? This is disappearance of hydrogen. Hydrogen. So production of ammonia is this guy, not including that number. So I have 1 over 3 of disappearance of that is 0.00200, and half of this. So my question is, okay, if you do math, you will get 0.00133. Any question?
Can you leave that for one more second?
Actually, yeah, maybe I shouldn't go too fast. Okay. So reaction rate is written just like that. So annual calculation will give us the unit reaction rate. So this is what we call reaction rate. But we have to distinguish between reaction rate and any other rate. For example, disappearance of hydrogen or production of ammonia, that's not reaction rate.
Oh, so you just,
So they are asking not reaction rate. They are asking production of ammonia.
and that's the same
Production
as
rate of
disappearance.
ammonia. Yeah. So that would be just only this quantity. And they also, we did in the question 1, disappearance of hydrogen. That will be just this, not including 1/3. So I put that number on here. And then to find out question mark, I have to multiply 2 both sides. Let's say we have some reaction. This is like a general reaction here. AB can be any compound, ABCD could be any coefficient. Now our reaction rate is determined by reactant only. Product has nothing to do with the reaction. Now I would say Late law. So I'm not saying okay. Late law can be written in terms of reactant only, not including product. In the previous slide, we did reaction rate can be determined by whether you just monitoring product or reactant, right? Either way, you will get same result. But when you write rate law, we only use reactant. Okay? Because product has nothing to do with reaction. That doesn't affect reaction rate. Can you distinguish it? So you can monitor product to see what reaction rate is, but that concept does not affect rate. Are you comfortable with this? Is there anyone that you are confused?
I didn't really hear it. I was kind of half
Yeah.
reading along and half listening.
Yeah.
Could you say it again? I'm sorry.
So reaction rate is determined by reactant concentration. It's not affected by product concentration. But when you calculate the reaction rate, you could use product, you can monitor product concentration, okay? You can monitor it, but that doesn't affect reaction rate itself. So be careful about it, okay? Now also, reaction rate includes concentration of both reactant, in this case, because you have two reactants. You raise to the power that does not use this number, okay? When you did the equation constant, what you did is for this guy, let's this double arrow, equation constant would have been C constant raised to C power, just like that, right? If they are all in aqueous phase, you could do this. But when you do reaction rate, you do not raise this coefficient to the power. Why? That is because we do not know reaction mechanism. We didn't know mechanism yet. Mechanism, what happened behind the reaction. If this is elementary reaction, we use that A number here, B number there. Only if that's elementary reaction. Which means what you see is what actually happened, then you use AB here. Or sometimes when you see this, I use this reactant, and in the end I got the product. But behind of it, they may doing a lot of stuff, starting from here, going there. So if that involves a lot of steps, that's not elementary reaction. So most times that's true. That's why we cannot use this number here. Okay? We will get to mechanism a little later. So just think this number is different from A and B. Okay? Then you are responsible to find out this number. Okay, that number is not from here. You have to find this number through experiment. Okay. Now this n is considered as a reaction order with respect to reactant A. This m is reaction order of reaction with respect to reaction B. Adding those two numbers is what we call overall order of the reaction. Okay? And this constant K is what we call rate constant. Now this is the reaction we have. Well, reaction rate is given like that. This number happens to be same as this guy, or we do not have that number here. So this is determined by experiment, not by this reaction. Okay? Again, you are the one determine this number. Okay? Do not use that number. You have to determine what should go here. Okay? And then we'll do that in the later slide. So if this is the rate law, then this reaction is second order with respect to NO, and the first order with respect to hydrogen molecule. And the overall that is the third order. There's more example that reaction rate is nothing look like here, right? It's different. And this is the actual reaction law for this reaction. Same goes here. This is, although this is same, 1 here, we have like a fraction here instead of an integer. In this case, luckily, we have same number. That indicate maybe this is what actually happened. There's nothing behind. It's just, this is what actually happened. Okay? So let's say for this general reaction we have rate law as exponent n and m. Then to find out unit of rate constant, you can rearrange just like that. And the unit of reaction rate, this one itself is molarity over second. We did that, right? We did that in the previous slide. Reaction rate, whatever you use, that will always constant over time. So unit is molarity over second. Now unit of this guy, this is the sign of concentration, so there will be molarity of m's power, molarity of m's power, it will be this. So that divided that will be, so unit for rate constant will be m1 minus n minus m over S inverse. Okay? This is the unit. And then you should know unit. So what is the overall order of this reaction?
3.
3. 1 here, 2 there, so third order. So what's the unit of this rate constant? What's the unit of rate constant K? By the way, this rate constant K is lowercase k. Uppercase K means equilibrium constant. Lowercase k is rate constant. You have to distinguish it. Okay. What's the unit of K? Well, K is rate over H2 NO square. For unit, rate is mole over second, molarity over second. This is molarity of Q. So unit is m negative 2, that's negative 1. What's the overall order of this relation? You don't know. You don't know. Unless we are given a rate law, we don't know. Okay? So I wanted to distinguish between rate, reaction rate, and reaction constant. They are not equal. Okay? Reaction rate is written in terms of initial constant times sum of reactant. We could have 2 or 3, typically you have 2, and then raised to the power of n, that is determined by experiment. So this is reaction rate, this is rate constant. So you can see rate constant depending on the concentration, right? Rate constant is constant that's not depending on any concentration. Okay.
Could you say that one more time, please? The difference between K and rate.
Yeah. So reaction rate is written in terms of rate constant times concentration of reactant and the raised to power. So reaction rate itself depending on the concentration. But rate constant is independent of any concentration. So if you use different concentration of reactant to mix it, it doesn't matter you mix with more dense or dilute, rate constant stays same. It doesn't change. We just said this is a rate law. So reaction rate is written in terms of K and concentration. We call that as rate law. Okay, this is rate law. And more specifically, this is differential rate law. There's another thing we call integrated rate law. How many people have taken calculus so far? Calculus. Okay, that's okay. That is coming from calculus, but in this class, it's okay if you didn't take calculus. It's just safe. But the concept is coming from calculus. So this is what we call differential rate law because this rate law says that's equal to that, but at the same time, rate is defined by one of these. So for this specific case, it seems like these are our reactant, which means A mixed with B. We don't know, so let's say AB, that turn into something else. We have some product here. So if I use one of this law, rate is also equal to disappearing of A over delta T over 1 over A, and equal to negative 1 over B, delta B over delta T. So basically we are setting this will be equal to that. This is what differentiation is. It's a derivative of the calculus. Again, you don't have to know that terminology, but just notice anytime you have delta over delta, that's what the slope is. Slope is coming from calculus. Okay? You don't have to know calculus. That will be very helpful. Actually, if you know calculus, you can go a lot deeper. But we are not going that deep. So it's okay if you don't know calculus. Now, what integrated rate law is, mathematically, if this is the equation, you use integration technique to find out different equation. Okay? That's what integrated rate law is. We're going to show you example of it later. Yeah, that's differential rate law. You just said it. Now it's time to you decide when you have this reaction. I just said the rate law is depending on K and A, B, but you are not using this guy, right? You use different number, and I said you are responsible to find out this number. This is the question that is for finding M&M. Okay, so let's see how you find out. So these are the reactions we have. So rate law says my rate will be K times this reactant raised to certain number times chlorine raised to certain number. So we have to find out, you have to find the K, find out M, find out N based on this experiment. So this experiment data is given to you. If you do your own experiment, you also have to find out all these numbers as well. Okay? But that's for experiment lab. Here you are given data. Okay. There's a shortcut and there's already more detailed approach. Which one do you see first? We'll do both. Detailed approach. Right? So they learned experiment 1, and this is concentration they used for SO2. So 0.400 mK, and this is concentration for chlorine 0.400 N, and the initial rate is just reaction rate. Okay, we said initial rate, we said average rate, we said instantaneous rate. Initial rate is what we use to determine rate law. So that reaction rate come right here. Okay. I'm gonna well. From second data, my reaction rate is 0.0730 K 0.400 M 0.200 N. So why don't we divide top number by bottom number? Then I got this. K cancel with K. That will also cancel. So remaining thing is 0.400 N divided by 0.200 N's power. That will give me N's power 0.400 divided by 0.200, that will be 2 to the N. So if you look at this guy with that, my N is natural log 2 and this number. So in the logarithm, wait. No, sorry, not this. I'm going to use, either you can use a logarithm or natural logarithm. I'm going to use just common log. You don't have to use natural, although we could use. Therefore, my N is log on the bottom, log 02918, 00730, like that.
Where did your 2N come from?
So I divide by top equation by bottom one.
Yep.
When you do that, K cancel. This will cancel. So that one out as 0.40 N divided by 0.2 N. Now an exponent because it's common exponent, you can just take it out as common exponent and divide by that number by this. 0.4 divided by 0.2 is 2.
Okay.
So why don't you do this math? What do you get? Does anyone get number? Let's see. Log. I got 1.999, 1.999. But normally, so that's my n. Normally this is integer. Okay. So there was a little bit of calculation error or the standard error. So you could consider this one as just 2. Okay. So n is 2. We just determined n will be 2. Okay. Now let's use different data to find out n, right? To find out n, you could use these two data. So if you use these two, my reaction rate is 11674 equal k 0 initial concentration for SO2 is 0.400 n and m. And 0.800, and then we know n already, that will be 2. If you use bottom data, 0.5837, K, my constant is 0.2, and then we don't know m, constant here is 0.800, we know 2. Divide by top one by bottom one. K cancel, this one cancel. I have this, which means 2 to the n. Again, we do the same approach, take logarithm both sides. So n log 2 log 1.1674 0.5837. My m is log in the bottom, log this on the top, and then if you do math, what do you get? 1.1674 divided by 0.58, 377 divided by 2. I got 1. So m is 1. M is 1. So we just determined m and n from data. Now you're going to have to decide k. You're going to decide k. To decide k, you can use any data. It doesn't matter which one you use. So why don't I use the top one? So my rate here is 0.2918 times k. My reaction rate constant is 0.400, 0.400. I know power is 1. And the second constant is 0.400. And I know that constant will be second power. So my k is now just 0.2918 divided by 0.400. That will be q. So if you do this, 0.2918 divided by 0.4 so q, I got 4.56. Okay. And the unit is mole over second divided by molarity of third power. So that will be molarity negative 2 power and that's negative 1. Okay. So we have everything, k and n. So it's time to write rate law. So our rate law is, in the end, rate is K 4.56 times SO2 to the first power, CO2 to the second power. This is our rate law. So you need to find, you should be able to write your rate law once you are given data. Okay?
So you have to answer C before you can answer B.
Actually, that for the B, you can just use this guy, except this one has just K. So to answer B, this is the K,
Okay.
not just number. But once you determine rate constant is C, then rate law will be this. Okay? Because they ask rate law before you know the K, just it's okay to write as K, that'll be fine. But if they reversed this order, then write rate law as this. And then once we know the rate law, we can answer some other question. So for example, what if we use different concentration of this guy? So you can plug that number. SO to have this concentration, chlorine has that concentration. You plug in, you can predict what will be the reaction rate. Right? That will be D.
Does it matter, what position the M and N is? Like if M comes first versus.
Oh no, that doesn't matter. So you could actually use different order, that'll be fine.
Okay,
You can write chlorine first, but that should stay with chlorine.
okay.
It doesn't matter.
Is there a shortcut?
Oh, shortcut. Okay. I'm glad you asked the shortcut. You go through all of this to find out later, right? So you have to go through all of that to find out, this. So their question was determine rate law. So you just go. Oh, I don't have space. So this is your rate law at question B, right? You can find out this one very quickly instead of doing logarithm, okay? All right. So this is what we know. We don't know about number, but we know that M and N. So to find out reaction rate, find the N, this is nothing to do with chlorine, right? So this is nothing to do with chlorine. So find out some data where chlorine concentration do not change, which means chlorine concentration do not change between 3 and 4, right? If you look at data 3 and 4, this guy doesn't change. Only thing change is SO2 constant become double here. And then if you look at here, reaction rate double. Okay? So between those two data, chlorine does not change. Only thing changes this guy double, and that's when reaction rate double. Where supposed to be 1. This is double. First power will make it double. So you already know M equal 1. To decide the N, SO does not change. Find the data there where SO does not change, but CO2 change. So you can look it up this data, 1 and 2, or 1 and 3, or 2 and 3. Doesn't matter. So let's look at 1 and 2. SO do not change. When this guy double, this quadruple. Do you see it? When this guy double, this quadruple. So when this guy double, this becomes quadruple. That means this is supposed to be second power. So N is 2. Are you comfortable?
Will we always get the little chart of data? It won't work if they just give us like one line, I guess. or-
No, they shouldn't give one line. If you have one line, you cannot determine this. Okay? You'll be given a bunch of lines. Okay? So that's a shortcut. Is it shortcut really short for you? Is it shortcut really? That's a shortcut, right?
I will be after I speak with you after class.
Okay, you can ask me anytime. That was the last slide. So I'm going to stay here. You can ask any question, okay? I'm going to stay 30 more minutes. You can ask any.
What? You should have those, all of them. The only, I haven't uploaded this one, obviously. Or, I thought I had uploaded.